Chris, thank you for joining me this morning, and I really appreciate your time. I know you guys are out West Coast, so early morning, 8 a.m. call with me, much appreciated. I
No
just wanted
problem.
just wanted to get the ball rolling here and get your title, your history, your resume, basically what got you going with Menlo Micro.
Okay, great. Yeah, so my name's Chris Giovanniello. I'm the co-founder and senior vice president of marketing at Menlo Micro. And I've been working, so we launched Menlo in 2016. So I've been working on, as part of Menlo for almost 4 years now. But prior to that, I was 5 years at General Electric working in business development within GE Ventures, which was the corporate venture capital arm of GE. And it was in that role that I came across this technology that GE had been developing for these very high power, high performance micromechanical relays. And between 2012 and 2016, about a 5 year period, I was working with our now CTO, Chris Giovanniello, and trying to license the technology out of GE. That was my primary, business development activity, was trying to license technology that GE did not want to fully commercialize internally. And
You wanted to outsource the technology to a third party.
well, they had because this is it's a unique process, and so GE had developed the process internally in their research fab, and that was one of the things that even when I went to work at GE, I didn't realize how much they had done in semiconductor process development there. But so they developed the process, and actually got it to a quite mature level over almost 12 years of development from 2004 to 2016 at GE. Got it to the point where they had developed we had developed some initial products that got designed into MRI systems within GE Healthcare, replacing pin diodes. And so it was quite mature. The only challenge was it was on 4-inch wafers. It's a research fab, so it was not very cost effective and not something that you could really build a scalable business around that fab. And so I think we finally were able to convince GE that, look, if you want to get access to this technology and use it and make it less expensive and more, kind of a traditional component that you're buying from a regular supplier, we really need to find a different way to do this. And that was really the genesis of Menlo, which was set up a company that really focuses on commercializing this, not just selling it to GE, which was, relatively speaking, a pretty small market, but sell it to the world. And that'll help to drive the volume, drive the scale, and drive down the cost so that GE could get access to it much less expensively, without GE having to spend all the capital to do that. So that was how it came to be.
Very nice, very nice. And before we get into like the construction of, I guess, like the secret sauce of the switch, was it basically the MRI application that drove the development of this switch?
Interestingly enough, no. It first started back in 2004 with some discussions with the what used to be called GE's Industrial Solutions Group. So it was the organization that developed circuit breakers and relays for industrial control. So, low voltage, medium voltage, high voltage for factories and transmission distribution. So very, very high power, high voltage stuff. And their objective was to try and replace traditional mechanical relays with something that was micromechanical, to be able to do things much faster. So extremely fast and small protection. That was really the impetus that got it started back in 2004. And then for a variety of reasons, it transitioned over to the healthcare application being a much quicker path to entry and the ability to turn it into a product. And so it kind of went in that direction somewhere along the way.
Yeah. You kind of touched on there a little bit, but could you dive into a little bit deeper of what exactly is a MEMS switch?
Well, we've actually branded this technology, we call it the ideal switch, and really what it's doing is it's trying to address some of the major compromises that exist between, on the one hand, the traditional electromechanical relays, which have been around for almost 200 years. So, very, very old technology, and hasn't changed significantly in terms of how it works in, probably close to 100 years. So you have mechanical relays, which are large. They're very slow because to switch a mechanical relay, you have a big piece of metal that has to move from point A to point B. So you have to put a lot of current to drive a coil that creates a field that makes the metal physically move. So they're big, they're slow, and the other challenge with relays is that they don't last very long. So that action of turning them on and off over a period of millions of operations, they wear out and you have to replace them. So then on the other hand, for switching, you have semiconductors. And semiconductors are fantastic in addressing those key shortcomings of mechanical relays in terms of they're small. You can make them very integrated. You can manufacture them on wafers, so they're very easy to scale up in volume and then drive down the cost. They're extremely fast, and they're very reliable. They don't wear out unless you really, really beat on them or put them at extremely high temperatures. So, solid state technology and transistors, when that started to appear in the 50s, 60s, et cetera, started to replace a lot of relays. However, there's really one major shortcoming with the semiconductor devices is that, and the hint is in the name, it's a semiconductor. So it's a non-ideal signal path. You have losses when the signal is going through the semiconductor, when it's turned on, and then that generates heat, especially if you're dealing with very high current. And when it's off, you still have a leakage path because everything is still connected. So, that was our objective with the ideal switch, or what's in many cases called a MEMS technology, is to really have the key electrical benefits of the mechanical world, which is extremely low loss when it's turned on. You have a metal-to-metal conductor, and then when it's off, you have an air gap. So you have those attributes of the mechanical relay, but all the other aspects in terms of the size, the speed, the reliability, we borrow more from the semiconductor world in that regard. So that's the overall construction.
Okay. Going into the history of MEMS technology, just from conversations with trade shows and other design engineers, RF engineers, why has it taken so long for this technology to really mature?
It's a good question, and it's a question we get quite frequently.
Because when I bring up on my line card Menlo Micro, and I go into MEMS technology, and they're like, "Oh, MEMS, we've tried that a decade ago, it didn't work. Why does it work now?"
Yeah, so it's a good question. There's been efforts to try and fabricate this type of a micromechanical relay going back really to the early 1980s. So you're almost talking about 40 years. There's been various research efforts and some commercial attempts. What's been the real challenge has really been one of reliability. And what was unique at GE that really hadn't happened before were two things. One, GE has a significant amount of experience in reliability, engineering, failure analysis, and most importantly, material science and metallurgies. And one of the first things that we discovered at GE was, or the first activity was not to develop a micromechanical relay like this. It was actually to assess the problems with other MEMS or micromechanical relays that were in the market at the time, and to understand why they failed. And almost to a T, they all had issues with the materials that they had chosen to build the mechanical actuator. And so GE went off on an effort to actually come up with an alloy that would be specifically well suited to the function of a mechanical relay, which is you want the beam to be very low loss, highly conductive, because you're going to be passing a lot of current through it. And at the same time, you need it to be extremely robust mechanically. So when it's opening and closing, when it's subjected to temperature, you need to make sure that it retains enough spring force so that when you release it, it will have enough mechanical strength to spring open. So that was, I'd say, really the key thing was a material science investigation at GE, the ability to really look at this from a blank sheet of paper. A lot of the other efforts to resolve or come up with micromechanical relays in the past, they were done by fabless companies that had to use the materials that were available and whatever fab they chose. GE didn't have any of those constraints. They were able to come up with the material set on their own.
Those previous switch companies, they were more of a Me Too company instead of actually developing new technologies because of their fabless.
Yeah, some of them were spun out of universities or stuff like that. There are actually some pretty large companies, commercial efforts. Omron spent a number of years. And there's the startups or the fabless companies had a lot of struggles because they just didn't have access to the manufacturing flexibility that we had at GE. And then some of the more established companies like Omron, RFMD had a long-running effort. Advantest. There were a bunch of established companies. I think it was really an issue of the time. A lot of companies who are running for profit and need to return results on their investment in a short time period, maybe 2 years, 3 years, 5 years max. If you can't come up with a commercially viable product in that time frame, a lot of those programs get shut down.
Yeah,
and so I think,
GE in your corner helps in that aspect, right?
Yeah, so GE, we were really fortunate because GE was, very long-term thinking and also had multiple internal businesses that could help to fund it. And like I said, if GE hadn't invested, 12 years and close to $50 million to get it just to the point of a mature product, that stick-to-itiveness and that long-term thinking, I think was really the other key attribute that this takes a lot of time and money and engineering to solve some of these fundamental reliability and material problems.
Yeah, I was very excited when I realized you didn't have a rep in the Mid-Atlantic, and I jumped on the opportunity, but I think I was a little early to the game because you were still in that phase where you were branding and making actual part numbers, product, and you were really defining your product line. And
right.
The golden child is now the MM5130.
Right.
Okay. And could you dig a little deeper into what the MM5130 is? And maybe if you want to touch on some of your part numbers, frequency range, power handling capabilities, maybe on how you, why you develop new part numbers or advantages and disadvantages of each.
Okay. Yeah, I think the primary thing that we're focused on right now is the release to production of our 5130, which is the one that's over my shoulder here in the picture. It's a high power SP4T RF switch, can handle from DC to up to 20 gigahertz, slightly above that if you do some custom matching. But really what everything that Menlo is doing is 25 watts and above right now. So that's one of our key attributes, is that these devices, while we can make them extremely small, they can handle a significant amount of power, even CW, continuous wave power. So everything we're doing is 25 watts and above. In this device here, what's unique is really the power density. So you can't, in the semiconductor world, it's really hard to get a significant amount of power handling like that, and at the same time a large number of channels. So you see high power, SPST, SPDT, pin diodes, In some cases with GaN, you can get a 50 watt, 100 watt switch, but it's really hard to get significant power handling with an SP4T or SP6T, SP8T. So that's really where we shine. Extremely low loss because that device there's no transistor in the path, so you have no nonlinear attributes in the signal path. It's really just it's a small switch that spans a gap over a nice 50 ohm transmission line inside that package. So it's that's why we branded it the ideal switch. The other thing you can see in the picture there, I don't know if it's clear on your screen, but the unique packaging that we've developed for this is an all glass construction. So if you think about it, we have a metal switch that's embedded in a glass package with an air cavity with just metal traces coming out of it. So you have a really very high isolation substrate, which means you don't have any coupling through the substrate to reduce the linearity. That's really a key limitation for switches that are built on silicon, is that you have losses and linearity degradation due to the substrate itself. So glass is really ideal for that type of a device.
Does that construction help with any performance over temperature?
The thing that, not so much the glass, I think the thing that helps us the most on the temperature is, again, there's no transistor. So if you look at a data sheet for any semiconductor switch, you're going to have curves, the insertion loss and all the different characteristics. They're going to change with temperature due to the varying performance of the transistor or the FET that you're using, right? There's a junction temperature. So we don't have that. All we need to deal with is the change in the bulk resistance, really, of the metal that we're using in our device. So, we have some charts that you've seen where, over a temperature range from, say, -40 to plus 150 degrees, very little change in insertion loss, maybe 0.05 dB of variation, which, is probably 10 times better than what you'd see. You probably see a half a dB or more with a semiconductor-based switch over that temperature range.
Okay. So there's all these advantages and applications for applications that obviously for GE, other applications for mil defense and aerospace. What kind of niches are you finding yourself in?
I'd say there's a significant positive response for really marrying this technology up with software-defined radios, so very frequency agile radios that need to have high power RF front end that can tune from, all the way from HF bands up to 6 gigahertz and even beyond. And so we're finding a lot of applications in things like tunable filters, switch filter banks, tuning of impedance matching networks.
You just had a presentation on your virtual IMS for your tunable filter, correct?
Yeah, we're actually, we're commercializing right now one of those filters, the 6005, which is a 7-channel UHF switch filter bank. It's got extremely low loss, and one of the things that this also allows us to do is make things a lot smaller. One of our claims to fame is really looking at applications where we can bring significant reductions in size, weight, and power, which is a big deal for, especially on the military side, but also many other markets. That's become a key attribute. So when you're trying to add more frequency bands and, you have these radios that need to support, 10, 15, 20 bands and still handle high power, that's where we can bring significant benefit by reducing the size and the losses in the radios.
Besides military defense, can you touch on any applications like Internet of Things? Any cool commercial applications out there? I think you mentioned in the past digital thermostats. I don't know, just any cool applications that, for everyday use, not just military defense.
Right. So we are on our roadmap. We do have plans to move more, not just on the RF side, but to also deploy this into more traditional power relay applications. And for that, I mean, line power, AC/DC voltage switching, replacing relays. I mean, that's really the place where relays are still the primary technology that's used. There's billions of relays. Even the circuit breaker in your house is a type of manually settable relay, right? All mechanical. So that's one of the nice things with this technology is that you can design the interface to our ideal switch. If you design it with really nice, well thought out RF transmission lines, then you can get a really nice RF switch, but you can also use these to handle power. So it's kind of a universal building block. So there's products that we're looking at there. We actually have a prototype that we're sampling with some partners right now, the MM9100, which is a 150 volt, 10 amp power relay built using it's a massive array of these small switching elements in order to handle the current. So it scales very nicely to go to 10, 20, 50 amps, even higher. You just have to put more of them, and the fact that they're really small means you can still handle a lot of current in a very small space. So yeah, power relays, they're home automation, smart thermostats, smart plugs. That's probably more on the consumer side. Your car is loaded with relays and fuses, as most people know. Sometimes they need to be replaced, and that they can be a point of failure in the vehicle. So that eventually is another application. EVs, I mean, the electrification of everything, whether it's in electric vehicles or renewable energy, and DC microgrids, and how electricity is going to be generated and distributed going into the future. There's still these very old relay technology that's managing how all that electricity flows, and so there's a huge opportunity for us longer term in creating more smart interconnects for equipment and distributing electricity, both in home and industrial environments. That will be a huge market for us in the years to come.
Mm-hmm. So you guys have this amazing technology. You're backed by some pretty large companies. You guys are in development for research and development for new products. And you guys, on top of that, market extremely well. We were kind of touching on this before we started hitting the record button. But how are you guys branding your technology? I see a lot of YouTube videos. I see a lot of virtual webinars. What is driving that?
Well, it's interesting. So, one of the big shows for us over the last couple of years has been the IMS MTT show. We had a really...
I wonder if Atlanta's going to happen next year. I mean, I think they're saying it's going to. I think that's what I just saw.
Yeah, it's been really interesting to see it evolve. I mean, we had a really great show in Boston last year. We brought a lot of hardware and a lot of live demos, and had a really fantastic show. We were planning for this year in Los Angeles to kind of amp it up and do even more, and then COVID hit and changed all the plans. So what it forced us to do is relook at how we're doing things, and so we took all of our demos and essentially set them up here in the office. We took over a conference room and set it up as kind of a media center where we could run live demos with webcams and through Zoom or Teams or whatever. And so it was, I think, a really good forcing function, because it forced us to set up a lot of these, digital demos and our ability to do webinars. And I think it's actually allowed us to get even more reach and exposure by focusing our efforts through digital means. And I think we'll probably end up doing quite a bit more of that in the future. And I think hopefully some of the trade shows come back, because there's a lot of great networking that you can do at those that you can't do over Zoom. But in the meantime, it's yeah.
Have you been traveling at all, visiting customers, or has it just been no?
No, but I mean, what was really good is that, we developed all these digital demos for MTT, and, because of the timing of it, that some customers couldn't make it. It was at, off hours. And so we've actually done more demos since MTT, just one-on-one with specific customers. So, rather than going in to visit, we're doing a 1-hour meeting where we can cycle through the demo with the camera and actually show, the screenshots of the VNA and all the actual measurement performance, but physically show what we're doing. That's been, very effective. We're getting a lot of good feedback from customers and from our sales partners that it's a really, good replacement for being there in person.
And evaluation boards are available through Menlo?
Yep. Yeah, we've built up our stock of eval boards for the 5130, also some of our power relays, and some of the other products. So yeah, we're in good shape from a sampling and evaluation perspective, and we're actually through the first phase of our conditional qual for the 5130. So I mean, we're on the verge of full release to production for this part. And getting our manufacturing line qualified for production. So that's a huge milestone for us as a company to be able to release to production our first product.
So I know the answer to this question, but I get it all the time from customers. Distribution, yes or no? Or is it direct through Menlo?
Distribution, you mean like through a Mauser, Arrow, or those folks? Not quite yet. I mean, we've got a lot of touch points right now with customers, as you know. The thing with distribution is you really need to be ready to support on a massive scale. And we're still a small company. We're growing quite a bit, but we're at 33 people right now, and so we're taking what we call a crawl, walk, run approach. We want to get the initial product solidly designed into the market, ramping in production, and we'll go down that path when we feel we're ready to support the what that would require in terms of the being able to respond, right? Because those channels immediately get you potentially thousands of engagements going on, and so I think from a manufacturing perspective and a support perspective, I think over the next 12 months or so, we'll be starting to look at that as things roll out. But we're in no urgent hurry to get that set up right away.
Okay. And what is actually one question? Menlo, I'm guessing that comes from Menlo Park. Is that right?
The name?
Yeah.
Yes, but you might not know which Menlo Park. So there's actually two Menlo Parks. The first one is Menlo Park, New Jersey, which I guess if you're East Coast, maybe that's the one you know better. But that was the headquarters for Thomas Edison's initial R&D labs, right, which eventually became General Electric when he moved the company up to upstate New York in the 1890s when GE was formally pulled together. So the Menlo, on the one hand, is a nod to Thomas Edison, inventor of the circuit breaker. He patented the first circuit breaker and founded GE, and so it's really a nod to our GE roots. On the other hand, GE Ventures, which was the group that spun this out and initially funded it, GE Ventures was based in Menlo Park, California. So we had two Menlo angles, both tied to GE, that was kind of the genesis of the Menlo Micro name.
Okay, very nice. Well, I think this cleared up a lot of things, and very good idea to just do a broad overview. I mean, we're talking high power switches, extremely small, power consumption. Actually, one thing we didn't really touch on was switching lifetime. We're promising what, 3+ billion switches? What are we approved? What's your line for switching life cycle?
So yeah, that's our minimum spec, and that we're going through that qualification right now. So we're going to, for the initial products, we're going to be guaranteeing a 3 billion cycle lifetime. Some will last much longer than that, but that's really the you need to guarantee a minimum.
Yeah.
So yeah, we've had customers that have tested some of these that have cycled them out to 20 to 25 billion. So you'll see some that last that long, but minimum requirement that we're meeting is 3. And we know why the 3 billion is the limit today, and we know how to extend that. So over the next 12, 18 months, we'll be starting to provide some enhanced version of the products that go beyond 3 billion. We're going to be pushing in the next phase to hopefully to a 10 billion minimum, and our goal longer term is to see if we can get it up to 20, 25 billion minimum. I think when you get to that level, then a lot of the people who are concerned about lifetime and wear out, you kind of get to the point where it's safely, it's really no less reliable than a semiconductor at that point, because you also have semiconductors that when you heat them up and put them under various conditions, they also eventually start to break down and wear out. So that's really our goal, is to kind of get to that 20, 25 billion number, and then hopefully we don't have to talk about cycling anymore. It's a non-issue anymore.
Yeah. Resource-wise, I love your YouTube videos. I love your webinars. Is there anything else you would direct anybody listening to this video to go to? Any white papers, any links, anything in particular on your website you would want to direct them to?
Yeah, I mean, there's quite a bit of information on our website. So we have data sheets for all the core products, but we also have a really cool, for people who want to get a little bit more into the background and some of the more detailed, the physics and the material science behind it. There's a resource center on the website. I think it's on, is it under the support section? Let me just look real quick so I don't misspeak. Yeah, under the company section, there's a category called Resource Center. Mm-hmm. And what we've put there is, because this has been developed since, like I said, 2004. So there's quite a few technical papers, many of them written by GE, some written by Menlo, some written by partners, Corning, which we mentioned the glass. Corning has done a lot of work with us on the packaging. So there's a lot of technical papers and presentations that people can take a look at to learn, get a little bit more under the hood and understand more how it works. So I'd say that's another good area. We're also going through a pretty big overhaul of the website to improve it even further. So we'll be rolling that out in the fourth quarter, but it's going to have a lot more information available for for customers, for partners, et cetera. So it'll, we want to make it a lot easier to scale the support by providing things, in a self-service fashion, so that people don't have to, call or email with every simple question.
Yeah. Hey, and your reps are always a good resource, right?
That's right. We want to enable you so that you can answer all the questions.
Exactly. This is a good time to do this stuff, to get your back-end process set up when you're not able to travel as much. And, get your, papers, update websites, do your webinars, do your YouTube videos, do interviews like this. So when you can start hitting the streets again, you're ready to rock, and you can just refer to your resources. So it's a pretty good idea to do that. So I think that kind of wraps it up. And I really appreciate your time today, Chris. And you have a great product. And I think once the word's out, it's going to be, the floodgates are going to open. So please share away. When I post this on YouTube and LinkedIn, please share away with all your friends.
Absolutely. We'll do that as soon as you post it.
I will. All right.
All right.
Thank you so much.
Thanks, Paul. All right. Have a great day. Take care.